Great, so now we've moved on to section 3.3. Now we're going to be talking about the spread or the variability in a distribution. So I have again our sample data set of gas prices. And our idea is, if in the previous section we were trying to come up with notions of average, right? We were computing average or competing averages of a gas price. But here's another way of thinking about it. What if, we are randomly assigned, or we happen to randomly find a gas location. We're running out of gas. We need to find a good price. But given all these different possible gas prices, right, what do we expect would be a normal range for the gas price that we might encounter, right? So you're driving down, I don't know, Watt, and you find yourself at Arco. What could the gas price be, right? It won't be any lower than $2.99 maybe. It won't be any higher than $3.39 you hope. But so then what is the usual range of values? That notion is the idea behind variability. So how do we measure the spread of a distribution? The two most common ways, and these are the ones that we're going to use the most, are variance and standard deviation. Variance and standard deviation as statistics are very important, not only here, but in later sections and later units. And pretty much every modern computer can handle the calculations. So we'll start with variance. Whoops, that's not how you spell it. And it has different forms depending on whether you have a population or a sample. I'm going to show you the sample variance, and it's different for the population. You should go to the textbook to see that formula. It differs in just one important way. And the formula for the sample variance is you take, so this symbol right here, S squared, that stands for sample variance. You have the sum of these expressions. Each data value minus the mean, the sample mean, squared. That sum divided by n minus 1. So let me clarify what all this is, right? So this is the sample mean. And this expression right here is what we sometimes call the squared deviations. By deviations, we mean how far away we are from the mean, from our notion of average. So think of that sample mean as your lodestar. That's your center point. And we measure how far away each data value is from the sample mean. You add up all the squared deviations and you divide by how many we have, minus 1. So n is the sample size, and we subtract by 1. The reason for that will be made more clear in a later unit. But this is different from the population variance formula because for population, we just divide by n, by the population size. So how do we calculate this? Well, literally what we're talking about is we take our x1, subtract the mean, squared, plus the next value minus the mean, squared, and go on until you find the last data value, subtract that from the mean, square it, and then divide by the sample size minus 1. And you can use a calculator. You can calculate this by hand, but importantly, you do usually need the sample mean first, right? So if you recall, we found that the sample mean was roughly 3.22. Was that right? Or was it 3.20? Yeah, it was 3.22. Had to just check. And so all of our data values, we're going to evaluate them by subtracting 3.22 from them and then squaring that. And what you'll get, and this is very fun, you can set this up in a table here. So each data value, right? And I'm just going to set up the first few, just as an example. So 2.99 and 3.01. You would do this through the whole list, and you can do it in Excel or Google Sheets, or even your TI-84. Then you subtract the mean. So when you subtract the mean, you're subtracting 3.22. So 2.99 minus 3.22 is minus, what would that be? I get negative 0.23. Okay, so negative because my data value is left of the mean. And then if I do the same thing for 3.0, I get negative 0.21. As you go down your list, you'll notice that you'll get negative deviations until you get to just around where the mean is. So none of our data values match exactly with the mean, but at some point, the deviations become positive. The problem with just working with the deviations is when they're negative and positive, they can cancel out, and then you don't get a clear picture. So what we do next is we square all of those values. So we take literally these deviations and we square them. So I would get, 0.0529. So that's the square deviation coming from 2.99. And similarly, 0.0441 from the 3.01. And so what happens now is when you square these small values, they can either get much larger or much smaller, depending on whether it's less than or greater than 1. And as you get closer and closer to the mean, the data values that are closer to the means have smaller, much smaller square deviations. And then lastly, you would add these all up. So the sum, oops, not what I wanted. You would add these all up. And divide by your sample size minus 1. That said, usually there's a formula for finding a variance. If you are using your TI-84, on a TI-84, the function that you want to use is you want to use one var stats, and you will get the S value, whatever that is, and then you have to take that value and square it. In our case, I just calculated it right now using Google Sheets. The function for Google Sheets is var.s. Then I get 0.0146, roughly. I could probably go another digit of accuracy here, but I'm going to start there. So, one really important thing to note about variance, though, is that whatever the units were for your original data set, our original data set was in dollars. This is in dollars squared, which makes it hard to interpret in terms of the data set itself. It's hard to compare the variance to the data, the raw data. One other thing to note about the sample variance is that it is actually highly sensitive to extreme values, because if you have some value that's very far away or very different from your mean, then it contributes a very large squared deviation. So the smaller your variance, the tighter or the less spread out your distribution is. So here's a sample distribution. Here's another. the taller the peak and the narrower the peak. So we have a smaller variance, actually smaller variability than this one. So variability is different from variance in that variance is a specific way of calculating variability. But we have an improvement on variance, which is standard deviation. And standard deviation, pardon the pun, is the standard. But what's so great about standard deviation is it's literally the square root of the variance. So you take, again, the sum of your squared deviations, divide that by your sample size minus 1, and then take the square root. Hence why we have this relationship. S squared literally is the square of S, right? And vice versa. S is literally the square root of S squared. So the notation there is not by accident. Again, if you use one var stats, that S value, that's your sample standard deviation. And you should always be careful that you're using it for a sample, not a population. Having said that, let's calculate it now. I'm using Google Sheets again, but I find that the standard deviation of my data set is 0.121 roughly, and that's in US dollars, right? So in other words, my one standard deviation is 12 cents. And this will be important, as we'll discuss in a later section, about how to gauge our expectations about what's a normal data value in our data set and what isn't. We have to meet some specific conditions for our data set, but it is actually very versatile and we'll use it in a lot of different situations.